So guys, welcome to the third video of the series, the atomic models. And this atomic model will be, let me just increase the points of these. Okay, one, and okay. So now this first atomic model we reviewed was about J.J. Thomson's watermelon model. You can look it at the previous video, and now we're going to look at the atomic model of Rutherford. So what's the name of his model? Well, his name of the model is very fancy. It is called the gold foil experiment. It was known as the gold foil experiment. He used the gold foil and alpha particle to determine the positions of the protons and the electrons. So the protons, we are calling it is not been discussed yet, but let's say the positive charge. Okay, so Rutherford found out the positive charge location and the location of the negative charges. So let's get straight into it. So what is alpha particle? The first question. So alpha particles, it's basically a helium 2 plus atom. Helium 2 plus atom was discovered back then. It was called the alpha particle because it had a great attribute to it. So we know helium is 2,4, right? So that means it had 2 electrons, but it lost the 2 electrons. So it is now dipositive. That means it is twice the positive charged. And that dipositive atom is called the alpha particle, which is positively charged. And why did he use it? So we knew earlier that in the atom there is a positively charged part, and inside there is a negatively charged part roaming around. That was told by J.J. Thomson in his watermelon model, that the red part, there's the positive part, and the black part, there is the negative part. So he thought about it, and he found that if we strike, let's say we strike this atom with alpha particle, what will happen? So alpha particle is just, you see, positively charged, right? So it would get attracted to negative charged and get repulsed by the positive charged. So if Thomson's model is quite accurate, we would see that as the outer part is positive, so they will go in and they will come back repulsing the alpha particle. So that the phenomena that will happen if the outer part is positive. And if the outer part is negative and inner part is positive, what will happen? So the positive charges will go get attracted to this part. And that was his theory. That's how he carried out his experiments. So let's see his experiment in details. So he set up a radium launcher. So that's the launcher for alpha particle, right? This is a gold foil. And why did he use gold foil? Because you see, gold has a higher positively charged level, and so it has less chance of getting collided with the alpha particle and changing into some different reactions. And it can be made very thin, so it was very helpful for him. And he put up a screen. And this screen is the zinc sulfide screen. So by zinc sulfide screen, we can locate where the alpha particle is going after getting hit. So his experiment started, and he started hitting the alpha particles, and some of the alpha particles went right through. Not some of them, many of them, most of them went right through. And some of them got deviated. They were right there and they deviated in an angle. They deviated. Okay? And some of them, very small amount. I'm going to do that in a different color, it's a red color. Very small amount hit the gold foil and came back 180 degrees. Very small amount, just like 1 out of 20,000. It occurred, this phenomenon. So what was his conclusion based on these three phenomena? Let's say this is the one phenomenon. Let's get it a different color for it. This is phenomena 1, okay, and this is phenomena 2, deviating back, and this is phenomena 3. So what were his conclusions based on the phenomena? So from the first phenomena, he concluded that as the alpha particle is not hitting anything and it's going straight into the zinc sulfide screen, that means there is nothing present there. There is no positive charge there. There is no negative charge there. There is nothing there. And so the alpha particle is going straight in without having any problem or without getting deviated or something. So he concluded that most of the space is void. Most of the space is void inside an atom. So inside an atom, most of the space is empty or void. Now let's move on to the second conclusion he drew. So he sees that in the middle part or close to the middle part, some particles they deviate in an angle. They are deviating in a very weird angle. So he concluded that in the middle part there is a positive charge. So in the middle part there is a positive charge, and so when the particles are going in, they're getting repulsed by the positive charge and they're getting deviated. That's the second part. What was the first part? First part was there was nothing there, so it went right through. It went right through because that was empty. And the second part is deviating because there is a positive charge in the middle, right? So in the middle there is a positive charge. And what was his third conclusion? The third conclusion was very great. So you see that let's get this part. Okay, so 1 out of 20k chances is that the particle you throw will get back. So you throw a particle and it gets right back 180 degree. It's like hitting a ball to a wall. When you hit a ball to a wall, it will not deviate, it will come back, right? If you throw a ball to a wall. So that's what happened. And as the number of times that happens is very low, that means the area of the wall is low. The area of the positive charge is very low. It is very low. And if the chances were higher, let's say 10k out of 20k times we see, let's assume we see this third phenomena, that would say to us that the half of the part inside the atom is filled with positive charge. So that's why it is getting back 180 degree. But that does not happen. What happens is 1 out of 20k gets back. That means if we think of, let's say, a big massive area, of an atom, the positive charge will be in a very densely accumulated part, very small. So concluded that it is dense and small radius, the positive charged. And that's the thing he observed from his observations, from his experiments, and he gave his theory, his model, the solar system model. And in the next video we'll learn about his solar system model. So stay tuned.